All right, guys, good evening. It is 5 o'clock on Tuesday. So it is time for some Calc 2. So as you saw in the online lesson today, we're going to be looking at polar curves and derivatives with polar curves. We'll talk about polar curves a little bit, look at some graphs, and then look at doing some calculus with them. Be very similar to last Thursday with parametric. This is just a quick reminder, and I'll remind you again at the end. This is the last section in this module, which means you're going to have another quiz coming up, so make sure to pay attention on that on the calendar. On Thursday, we're going to move on to applications of integration, which will be pretty interesting, the stuff we're going to do. Okay. Well, with no further ado, let's jump into talking about polar equations. And we'll start with a quick little review of polar coordinates. I know you guys saw this stuff in the online lesson, so I don't want to spend a lot of time on it, but to see if there's any questions that come up. So we've been dealing with all rectangular coordinates up to now, but we have to be aware of polar coordinates, and we'll use them a little bit this semester, and we'll use them even more in Calc 3. There are times when things are easier to represent with polar coordinates. Now, rectangular, a point is represented as a horizontal and vertical distance from the origin, whereas polar coordinates only need the distance from the origin and an angle that is made with the positive horizontal axis. Okay. So what this looks like, we're very used to points having an X and a Y. Right, so we would go out to some point X, go up, and we'd have some Y. Well, in polar, we use the radius and the angle it makes with the positive X-axis. It will allow us to do some things easier in math than it would in rectangular. We'll talk about some examples of that. Now, all of our transformations come from right angle trig. All right, so nothing here should feel too new. Let's talk about where everything comes from. X is r cosine theta. Well, why is that? Well, remember, sorry about that. It came out a little big. X is over here. Cosine is adjacent over hypotenuse, right? So cosine theta is x over r. Multiply the r, and that's how you get that transformation. Similarly, for sine, it's the opposite. We have a right triangle. Pythagorean theorem tells us that x squared plus y squared equals r squared. If you want to solve that for r, you get square root of x squared plus y squared. And lastly, to get the angle, we look at tangent of y over x. Tangent relates the opposite over the adjacent, hence this formula here. Okay, so nothing crazy going on here. It's really just right angle trig. And, we're not going to spend any time on this because you did this in the lesson, to go back and forth. It's pretty easy to go from polar to rectangle. All you do is plug in your 5 for r and your pi over 6 for theta to get your point. Where things get a little bit interesting is when you have to go the opposite direction. So let's do this second one just for a little bit of practice, because there's one thing I want to point out. You're not going to have to do this a lot, but we might have to find endpoints of a graph. So let's talk about how we move a point this way. All right, so we've got the point -4, 5, which would be roughly about right here. And let me get my calculator open, because there's something I want to show you in there. Okay. So how do we get from this point to a polar point? Well, we need two things. We need distance r, and we need the angle theta. And we saw from the Pythagorean theorem, r squared equals x squared plus y squared. And we're using that point there. Let's set it away for a minute. Bring that back up when we need it. So r squared equals negative 4 squared plus 5 squared. So we have 16 plus 25, or we're getting that r squared equals 41. So r equals square root of 41. Not too difficult there. So if we're converting this over, we have square root of 41. And now we need the angle. And there's one thing I want to show you with the angle. Now we know that from a right angle trig, tangent of theta equals the opposite over the hypotenuse. This is negative 4. This is 5. So opposite is 5 over negative 4. Well, how would we solve this? We'd use inverse tan. So arctan of 5 over negative 4. Excuse me. All right, now let's see what happens when we put that in the calculator. So tangent of, we can put the negative out front. Notice I get negative 0.896 radians, or for this example, let's go ahead and use degrees, because there's something I want to just make sure we really get down here. So if we did it in degrees, negative 51.34 degrees. Well, measured from the positive horizontal, that puts me here. That angle there, roughly, there's our negative 51.34 degrees, or the negative 0.896 radians. We're not in the fourth quadrant, so it's really important that you know what quadrant you're in. Now, what we do know is if that angle there is 51 degrees, then this angle right here is 51.34 degrees, or 0.896 radians. All right, so what we do have is a reference angle we can use to find ours. In degrees, we would do the 180 minus that. Well, I guess since it's negative, we could actually go ahead and add it. So plus that answer. So that would be our angle in degrees. So 128.6598 degrees. But typically, we're going to represent our angle in radians. Unless we're told otherwise, we'll always be in radians. So I'm going to go ahead and go back and change back to radians. I just want to do degrees so that we can make it really obvious we're not in the right spot. All right. So now if we go back, now we're in radians. Again, we know it's not in the right spot. It's okay. This is just the way arctan works. Arctan is limited between negative pi over 2 and pi over 2. We have to turn it into a positive angle. So in this case, we could do that by taking 2 pi and basically taking off our reference angle, or since it's already negative, we can add it. So we know that our angle is 5.387 radians. And that's the one we would use in our point. Again, unless you're told otherwise, angles are always in radians. So I wanted to go through that just because that's a common thing that happens on these kind of problems, okay, for converting points. And depending on what we're going to be doing, we might have to convert points. We might not have to. Now, let's take a look at some polar curves. So I've got some here in Desmos for us to look at. Now, again, One of the nice things is some graphs are easier to represent in polar coordinates. For example, the graph of r equals 2. Well, if we were to think about what that is, that's the set of all points that are 2 units from the origin, which gives us a circle. This is a much easier way to graph a circle than even parametric. A circle is not a function, so we can't graph it as a function. We know from our conics that x squared plus y squared equals r squared, but that's a little more complex than just r equals 2. So for a circle, it becomes much easier to graph in polar. Now, what if we let r vary? So for instance, r equals theta, because now what's going to happen as theta increases, r increases. So if we think what's happening, our radius is getting bigger as we go around. We get a spiral, something we certainly could not graph in any other system. Might be able to come up with in parametric extension, but it's not easy in polar. Now, one thing I want to talk about with polar, you'll hear me use this term that, use Q because that's going to be used later. You'll hear me use this term that polar curves are created radially. Now, what do I mean by that? Let me show you. All right, so let's add. Actually, we'll just use one of the existing ones. So what do I mean by it's built up radially? Well, what I'm doing is I'm going to let theta vary from 0 to c, because I have a slider here that allow me to vary c. Watch the way the graph is created as c increases. It's created radially in a counterclockwise fashion. All right, that's going to be really important in determining limits, more so when we get into the next section when we're doing areas and arc length. But that's what I mean when I say these graphs are created radially. Let's do that again. So as theta increases, r increases, and notice it goes counterclockwise. That's always the case, just like the way we measure our angles in trig, quadrant 1, 2, 3, 4. Polar curves are created the same way. All right. I know, guys, if you have questions as we're going through this, as always, feel free to ask. We're going to look at a few other curves. So r equals a sine theta. Now, right now, a is set to 1. So this is just the graph of sine theta. All right. Notice what it makes. It makes a circle, but not centered at the origin. So it makes a circle at 0, 1. So this is another way of making some of our conics. Now watch what happens as a varies. We get a larger and larger radius. We make it negative, it goes below the x-axis. So having just our single trig function will make a circle, just not at the origin. Same thing with cosine. We'll play around with a little bit here. All right, now if we add a constant to cosine, this creates what's called a cardioid because it kind of resembles a heart. And watch what happens as b varies. Now we can make it have a loop as b gets larger. So a lot of really cool graphs. Now, you don't absolutely need Desmos to graph these. You can do these in your calculator. What you would do is when you go to mode, function, last time we changed it to parametric, this time we'll change it to polar. And so now when we go to y equals, it accepts a polar curve. So let's just put one in there, 1 plus cosine of theta. And now when you go to the window, here's the min and max for theta. Kind of like with parametric, you got to give it a range. There's our cardioid. So if we wanted to kind of match them up just to see, I think I did. Let's see, we did 1 and 1 for both. Let's make it a little bit more interesting. Let's make that a 2. There, now it's got the loop. So that would be a 2 here and a 1 for A. Okay, so we can graph these in our graphing calculator. You do not need to be an expert on polar curves by any means. You don't need to know the names of them. What we do need to be able to do is graph them and make sense of them. Okay, so don't worry about the names cardioid and some of the other ones that were in the lesson. Please do not think you have to memorize those. I just want you to know that they're created radially, be able to find endpoints, that kind of thing. We'll look at more of that as we work with Desmos. Let's see, what else can we create? We looked at that guy. This one looks pretty boring, right? You know, like we said, all right, if it's just cosine of theta, you get a circle. Here's where things get a little interesting. Let's make it a little bigger circle so you guys can see this. Now I put in a parameter inside of cosine. All right. Watch what happens as we increase this. Sorry, it increases really quickly on decimal. Now you'll see when we get to an integer, I can get it to stick on an integer, we get a much more stable version. We get this is called a 4-leaved rows. But when we get in those decimals, we get a lot of really cool stuff going on. Again, stuff there. We're at 3 rows. Every time we hit an integer, you can see it creates rows. But in between, there's a lot of interesting stuff going on at the decimals. You know, we could kind of fast, but you can kind of see it going through all those different curves. Do not get overwhelmed by this. We're not going to be looking at all these curves. You will have graphing utilities to help you out with graphs. I just want you to see what they look like. And again, changing C just changes the radius. It's changing that B that really starts to get interesting in the curves, but none of them went outside of that radius 2. This one will look familiar. All right, may not recognize it just yet, but watch what happens if I pull it over this way. We get our hyperbola. So this is a hyperbola as a polar function. As Q gets bigger, it gets a little bit straighter, it gets a smaller eccentricity, larger eccentricity. When it gets big enough, turns into right there, that one place, there's an ellipse. There's an, excuse me, not an ellipse, there's parabola. Then over there, it turns into an ellipse. And eventually back to, if we go to 0, it goes to a circle. Back to an ellipse, back to a parabola, back to a hyperbola. So we can, this will cycle through, this basic form will cycle through all of our conic sections. Not something we're going to do a lot with. I just wanted you to see it. Okay, now just wanted to see some curves, guys. You guys can play around with this as much as you like, because we can create some pretty cool stuff. Let's get into doing some calculus with these. And like I said, feel free to ask any questions. I'm gonna do one. It'll be kind of like last time. I'll do one, and then you guys will do one. All right, so I'm gonna do this guy here. Now again, remember I said it's grown radially. So I put a slider on there so you kind of see it created. So there's the curve. We're going to look at finding a tangent line for r equals, probably shouldn't, well, 2 minus 4 sine theta. We're going to find a couple tangent lines. Let's talk about how we do that. So what I want to do is bring up the lesson for today real quick and show you how we're going to use that to help ourselves. So here is our lesson for today. We'll go to calculus polar coordinates. This first part, guys, is using parametric equations to derive a formula for the derivative. You don't have to do this every time. It will absolutely work, but you can go right to the final version of the formula. This is not something you're going to have to memorize for an exam, so feel free to keep this with you at all times on a note sheet. Let's bring it over here so I'm not going back and forth. So basically, dy dx in terms of polar is going to be given by dr d theta sine theta plus r cosine theta all over dr d theta cosine theta minus r sine theta. You do not have to derive it again. The derivation's here. Where it comes from is all right here, leveraging what we did last time in parametric equations. All right, so we already know what r is. We also need what dr d theta is. So basically we just take the derivative of this guy. So dr d theta is the derivative of this with respect to theta to 0 minus 4 sine theta. The derivative of that is minus 4 cosine theta. So what does that make our dy dx look like? Well, we substitute in because we want this to all be in terms of theta. So dr d theta gets put in. So minus 4 cosine theta, sine theta. And we also plug r in. So 2 minus, whoops, forgot 4, excuse me. Minus 4 sine theta, cosine theta. And then again, almost identical. It's just a slightly different formula, and that's just because of what dx d theta is. So once again, we plug in the minus 4 cosine theta, cosine theta, plus, oops, not plus this time. It's minus. It's right there. Minus 2 minus 4 sine theta, sine theta. I wouldn't worry about simplifying this unless you have some reason. Sometimes they might simplify kind of nice. Or we might have some like terms. But ultimately, when you're finding a tangent line, we're going to be plugging in anyways. Let's see. We could simplify this a little bit. So we got minus 4 cosine theta, sine theta. Not absolutely necessary, but it might make things easier. Should be look a little more like a theta. Plus 2 cosine theta. And then when we distribute to this guy, we'll have minus 4 sine theta, cosine theta. That's going to be, we'll be able to combine some like terms there. On bottom, we got a cosine and a cosine, so that becomes minus 4 cosine squared theta. And if we want to distribute the sine, we're going to have minus 2 sine theta, because the minus from here, the sine from here. And then distributing here, we're going to have plus 4 sine squared theta. So we'll combine these like terms up in the numerator. So minus 8 cosine theta, sine theta, plus 2 cosine theta. Again, guys, I don't see this as a necessary step. Unfortunately, we have opposite signs here. Otherwise, we would have had a cosine squared plus sine squared, which would have been a nice Pythagorean identity, but it doesn't quite work out for us. All right. That's about as simplified as we're going to get. All right, I'm going to do a couple different tangent lines, and we'll check them graphically. First one we'll do, let's see. Let's do, we'll do a tangent line at theta equals, let's start with an easy one. Let's do it at 0. All right. So that means we're doing our tangent line with theta is 0. Our point of tangency is going to be like right in here somewhere. You can really see the graph. Okay. So two things we need for a tangent line: slope and the point that it goes to. Slope is going to come from our derivative. So basically our m is going to come from plugging in 0 for our thetas. So -8 cosine 0 sine 0 plus 2 cosine of 0. Now down underneath, we got -4 cosine squared 0 minus 2 sine 0 plus 4 sine 0. Guys, when you're doing this, because you guys are going to do this in a little bit, have your unit circle available. It'll make it easier than dealing with decimals, actually. I know it may not seem like it, but it will. Sine of 0 is 0. So that's 0. That's 0. That's 0. So when all's said and done, I've got 2 over a -4, because cosine of 0 is 1. So cosine squared of 0 is 1. -1/2. Well, it looks like if this is our spot, it looks like a negative slope makes sense. The other thing we need is a point that it goes to. Now, the way we get that, remember that x equals r cosine theta. I don't know why it did that. X equals r cosine theta. Y equals r sine theta. And basically our r, again, comes from here. And cosine, and theta is going to come from where we're finding our tangent line at 0. So we have 2 minus 4 sine theta times cosine theta, and 2 minus 4 sine theta sine theta. Now, sine theta is still 0, so this is going to come out as 0. Cosine theta is still 1. This is 0. So we have 2 times 1, or 2. So there's our point. The point 2, 0, which makes sense. We were looking at it about right here. So finally, we put together our tangent line. Y minus 0 equals -1/2 times x minus 2. We don't really need the -0 there. There's our tangent line. -1/2 times the quantity x minus 2. And there it checks out. We've got our tangent line. All right. So that's basically what you're going to do to find the slope and the tangent line. And you can use Desmos to confirm. I don't want to take up a lot of time on this because now you've seen one. But if you were to do, because if we were to do one at, say, theta equals pi over 6, I'm using the same derivative. I don't have to do any new work. All I need to know is what cosine and sine are at pi over 6. So -8 cosine at pi over 6 is rad 3 over 2. Again, this will come from your unit circle. Feel free to have it right next to you. Sine at pi over 6 is 1/2. Cosine, again, is rad 3 over 2. So 2 times rad 3 over 2. And I want to show you why this is better than using decimals, in my opinion. -4, we already said cosine is rad 3 over 2, just getting squared now. -2 times 1/2. Look at all the canceling that's going to happen. Plus 4 times 1/2 squared. All right. Watch how quickly this will simplify. Right here, the 2 and the 2 will reduce the 8 to a -2. And this 2 and 2 will cancel. So I have -2 rad 3 plus rad 3, which is just simplifies to minus rad 3. On bottom, This 2 times 1/2 is 1. 4 times 1/4 is 1. Minus 1 plus 1. We have a minus 1 plus 1. Those cancel. So on bottom, what do we have? This is going to be 3/4 times a -4. We have a -3. Those are both negative, so it's positive. So our slope is rad3/3. And very similarly, when we go to find our point, it's going to be the same as before. You're going to plug pi/6 in for here. And you end up getting, because pi/6 makes sine a half, 2 minus, well, 4 times a half is 2. Both these end up having 2 minus 2 in them. Our point just ends up being 0, 0. So our tangent line is at 0, 0 with a slope of rad3 comma rad/3. And there's our tangent line, and it works perfectly. Now there are 2 tangent lines at this point, which is something you're going to encounter in the worksheet, which is actually pretty cool. And so how do I know that this one came at pi/6 and isn't the other one? Well, pi/6 is roughly about 0.5. So look at when I'm at about 0.5. That's when I'm at this point. I don't get back to that point until theta is about, go all the way out here. Oops, I already passed it, sorry. I don't get back to that point until theta is right here at about 2.6, 2.7, which ends up being 5 pi/6. So 5 pi/6 puts us at the same point in the plane, but would give us the exact opposite tangent line. And as you can imagine, it's just the opposite sign. Okay. Questions at this point?
How did you get the x and y values when you were making the tangent line?
Or which tangent line?
The tangent line in green.
Okay. So the x and the y values, remember that for polar, our transformations are x equals r cosine theta and y equals r sine theta.
Okay, so they're just...
Yep.
Okay.
And I'll keep going through it just in case, because there might be other people who have the same question. All we do is we take that r and put it in for those r's, which is how we got this here. And then we plug in our theta and calculate.
Okay, thank you.
Yeah, no problem. Other questions? All right, let me show you what you guys are going to do in your groups. All right, I'm putting the worksheet in chat so you guys will have a copy. You're going to do 2 things, kind of like that. It's going to be very much like Thursday's class. All right. One is you're going to evaluate the sign, plus, minus, or 0 for these 4, and we'll do A together like last time. And then 2, you're going to do basically what I just did on the slide. So let's go through how to do this chart so you get a little bit of practice. Like I said, 2 is what we just did. All right, we'll do point A together, and then I'll have you guys do the other ones. Now these 3 are exactly like what you did last time, except now we're moving in the direction of increasing theta. So if we're at point A, increasing theta is automatically counterclockwise, okay? That is increasing theta. Remember, we talked about graphs being created radially. So at A, remember it's instantaneous. We want to say, okay, well, what's happening with x at A? Well, x is a little bigger here than it is after. So x is decreasing at A in the positive theta direction. We'll come back to this one. dy d theta. Well, as we move in the positive theta direction, we can see that y is increasing because we're going up. And for some reason I put a plus there and I don't know why. I said decreasing. So we have minus there, plus there. dy dx is a tangent line. If we imagine a tangent line there in our regular rectangular coordinates, we can see it would have a negative slope. Well, divide this by this, positive over negative is negative, so all that lines up. All right, now let's talk about dr d theta. This talks about the distance to the origin. Now at A, since we're on the x-axis, that distance to the origin is the same as x. So these are going to have the same sign. Where it'll get interesting is you're going to have to think about it at some of these other points. You know, is r changing? If it is it getting bigger or smaller as you move radially? Okay. So I want you guys to do the other 4 points in your groups so you can fill in your chart. And then see if you can find a tangent line at these 2 points and graph in Desmos to check. Any questions about what you're going to do in your groups? And you've got the worksheet there. So okay, we've got some time to do this. So call me in if you have questions or if you finish early. And we go over this stuff, okay? All right, you should have an invitation to a room.